everyone, welcome to part C of our video with the Lumerical IPKISS, and in this final part we'll showcase how to create a full PIC circuit using the components we have made, and then we'll also showcase how to get the transmission of the circuit and simulate it within IPKISS and the Python environment using S-parameter files. So what we're looking to aim to do right now is to create something like this image shown on the screen here. We want to take our contra-directional coupler device that we made in part B for advanced P cells and place it. We then want to place 4 more grating couplers and connect the grating couplers using waveguides to our device. And then the final result should look something like this, where we will have our grating couplers on the left, and then we'll also want to rotate our device by 90 degrees so it's vertical, and then connect the waveguides as such. And what we'll do here first is we'll go into our PyCharm again, and then in the example circuit I'll just make a new demo Python file. And to start off, what we'll want to do is we'll want to import our libraries once more. So starting with the PDK, so from sci-fab, we'll import all as PDK, and then we'll also import IPKISS, import all as i3. And then what we'll want to do is we'll want to import our contra-directional coupler device, so we can go back to our previous script, and at the very top we can borrow that relative import section, just to keep things nice and simple. And then once we have that, we know that the folders are now within the path, so we can do from designs, and then this time we'll look for the contra-directional couplers folder, and then we'll import the contra-directional coupler file as CDC. And we're good to go. So to start off in creating circuits, it's not like the other P cells. There isn't a structure for classes that you need to follow. We just have to instantiate the devices first. So we'll create the objects. There'll be a CDC object. It will be a contra DC. And then we can also create our grating coupler object. And here's where we're going to use the PDK. So the PDK comes with a grating coupler object, and it takes in a few arguments. So we can give it a line width, we can give it a period, and we can give it a number of periods. And then we're going to do our multi-line here to make it more readable. So line width, we'll just set it to 0.83. And then period, we'll set it to 1.2. And then the number of periods here, we'll set it to 15. And that should be good to go. And with that, we've instantiated our devices. So we can leave a little note here, instantiate the devices. So next what we want to do is we want to create these devices into instances. So what this means is we'll tell IPKISS how many of these devices are going to exist in a circuit. So of course, when we have one contra-directional coupler, both the grating couplers, we can reuse them. So we don't have to initiate more grating coupler objects unless these grating couplers will have their own unique parameters and are drawn differently. So otherwise, we can do a section here where we create a list called inst, and then in it we'll assign our dictionary values. So a CDC will be the CDC object, and then we'll have a grating coupler 1, and it's assigned to the grating coupler object, and then we can just do the same for the remaining other grating couplers. So we'll have 4 in total. We can go here, organize the code a bit, then we'll rename these GC2, 3, and 4, and they're all grating coupler objects. And with that, our instances are done. So next, what we'll want to do is we'll want to place the cells. And what we can do here is we'll create a array called specs, And then in the array, we'll call an IPKISS function called i3place. And then in place, we have to give it our instance object that we declared up here. So let's say we're going to place the CDC. And then with that, we also have to pass with it a position. So we'll just, actually, why don't we start out with a GC? Maybe that'll be easier to read. So start with GC1, and then we'll set it to 0, 0. And then what you can also do is you could pass an angle value if you want to. So for now, we won't pass an angle value for the GCs. We're going to have them positioned like so, starting from 0, 0. And then what we're going to do is we're going to base the GC off the connection point and make sure the distance between them is 127 microns for each one. And we'll move up from there. So with that, the first one will be 0, 0, and everything is good. We can then copy it 4 times. And then we'll place them accordingly. So the second GC here, it'll be at x equals 0, but this time will be 127 above. The third one will be 2 127s away. And then the final one will be 3 127s away. And we're good to go with our grating couplers. So why don't we leave that there for now? Let's try drawing it once we add more stuff, and then before we add some complexity. So next what we'll do is we'll also want to create something called an exposed port names. Port names. And this, sorry, let me check my code at the top real quick. Okay. Yeah, so this will be a list object as well, and then we'll basically tell the circuit which ports we want to expose so that they're shown. Otherwise, they're hidden within the circuit. And this is useful for connecting the circuit to other objects later if there are any. But in this case, just a general practice to do so in a demonstration. So in it, we'll create a name. The name will be GC1. And then in GC1, there is a port called vertical in. So we'll denote that with a colon here and then vertical in. It is case sensitive, so when working with custom P cells, make sure you're aware what the port is called. And then we'll bind that to port 1. And the reason is because we'll use this later for an S parameter simulation. So to keep the mapping easy, we'll just call it port 1. And then we'll copy it 3 more times for each of the other grating couplers we have. So 2, 3, and 4, they all have the same port name in the P cell called vertical in, so we don't have to change that. And then these will be port 2, 3, and 4 respectively. And then what we'll do next is we'll add all these lists that we've created into a circuit object. So we'll create the circuit called myCircuit. And myCircuit will be an IPKISS3 circuit object. And then what we'll need to give it is first a name. So we'll call it example layout. We then have to give it a list of instances, which we conveniently name the same thing. We need to pass it the specs, which we also name the same thing. And then finally, we have to give it some exposed ports. So this would be exposed port names. And with that, our circuit is ready. So to view our circuit, it's very easy. So at the very end, all we have to do is call our circuit object, myCircuit. And then we'll actually create a circuit layout object first. So myCircuit from the IPKISS circuit object here actually has a function called layout in the same manner that the P cells does. So anytime you need the elements or geometry, you can call a layout function like this. And that'll be it. Sorry, this is a dot, not a underscore. And then what we just do is we take our circuit object for the layout, and then we just visualize it, just like we did with the P cell. And we'll turn on annotate as well, just so we can see that our exposed port names are working correctly. And then you can also make a GDS while we're at it. So we'll do write demo.gds, and then we'll call it demo.gds, just so we can try to take a look in a bit. So I'll try running it, and we'll see if there's any errors. So what we should be expecting is the window to pop up and just show 4 of our grating couplers separated equally in distance, and then it should show the ports. So you can see here, everything looks good. We can kind of zoom in on it. So port 1, 2, 3, 4 seems to be properly indicated. And then we can take a look at our grating coupler that we took from the PDK. So it looks good. We also see that a CDC is made here. So perhaps there is a error in our code. Kind of makes sense if we look back at it. We instantiated the CDC object, but we didn't specifically tell it where to be placed. So it placed at a default, which is 0, 0. So we shouldn't be seeing that on the other ports as such. And then what we can do is we can also navigate to our folder here. So open an Explorer. And then we can try looking at the demo layout that we made. So here, demo.gds. This is a previous one I had. So here we go. We see that we have our cells made here. And our contra-directional coupler is placed for some reason here already. Might be because of a old file. I can give it a try again to see if it renewed, because I think I still have the figure open. So if I close the figure, it should do the final step of writing the GDS, and I should see it ask to update, which it did. So if I reload now, we'll see that it's acting as expected. So everything is good. So next, let's kind of add on to the circuit now. Let's place that contra-directional coupler maybe somewhere up here in between the 2nd and 3rd grating coupler. So we wanted to look maybe something like this over here, and then maybe we'll rotate. So what that will look like is we'll go back to our place cell section, and then this time we'll add in the contra-directional coupler. So i3.place, we want the CDC object this time, and the position we'll give it is 50 on the X, just so it's far enough away from the grating couplers, so that we can add some waveguides in a bit. And then we'll take 127 and we'll just multiply it by 1.5, so it's right in between the 2nd and 3rd grating coupler. And then we also want to try using our angle argument now. So angle, and then we'll rotate it by 90. And we can give it a whirl and see where we're at with it. So this time we should just see the CDC get placed into the correct spot. So this is good. We see right away that vertical line over there with the CDC. We can zoom in. Everything looks good on it. So seems like the code's going as expected. So next, what we can do is we can try to route in some waveguides in the next section, and then we'll connect them to the grating couplers and the device, and then we can build our circuit out and create a transmission response from the S parameters. But for now, thanks for watching.